99% of crypto trading bot fails. Not because of bad algorithms, not because of insufficient data. They fail because their creators skip the most important step: structure. Most people dive straight into coding. They focus on sexy parts like neural networks, technical indicators, backtesting. They completely ignore the systematic framework that separates profitable systems from the expensive failures. Today I'm showing you the exact framework used by machine learning engineers at companies like Facebook, Alibaba, Blockchain.com to build production machine learning systems. This isn't just theory. This is a battle-tested framework that will determine whether your crypto system will make money or loses it. Problem space versus solution space. Always start with the problem, not the solution. Before building any fancy machine learning algorithms, you have to understand what problem you're trying to solve. What most people do wrong? They say, I want to build a machine learning trading system, and then jump straight into, should I use transformers or LSTM or any other fancy deep learning techniques? The right approach would be to start with the problem space to identify the problem you're trying to solve. Don't say I want to predict exact crypto prices, or don't say I want to build transformers to make money. Instead, I want to identify Bitcoin trading opportunities or Bitcoin buying opportunities to build buy and hold portfolio by X% annually with a maximum drawdown of Y%. This is a well-defined problem. So do a reality check. You cannot predict exact crypto prices, you cannot make money with transformers, but you can identify probability distributions, relative value opportunities, and regime changes. And remember, ill-posed problems cannot be solved even with machine learning techniques. Accept this early or waste months. The design document. Every machine learning system needs a design document, and every trading system needs a design document. It's not bureaucracy, just clarity. There would be 6 sections in total, 1 or 2 pages, that would be enough. 1. Problem definition. Where did this idea come from? Be very specific. For example, Bitcoin tends to overreact to news and then mean revert within 48 hours. 2. Goals and anti-goals. So for goals, you can say something like 15% annual return, sharp greater than something, maximum drawdown less than something. For anti-goals, you'll try to say something like, I'm not trying to predict exact crypto prices. I'm not trying to take every trading opportunity. I want to stay in the market for X percentage of time, or something like that. 3. Risks. Here you have to define possible data quality issues, API failures, market regime changes, or any other risks that you may see for your trading system. 4. Success metrics. How do you even know that it works? Define the numbers and the metrics upfront. 5. Constraints. Available capital, computational budget, time commitment. And the last section is references, papers, libraries, blog posts that you are using. This document evolves as you build. That's normal, that's okay, that's even good to have a not fully written design doc at your day one. And remember, the design doc is not the goal. The working, profitable system is the goal. The design doc is your map to get from nothing to a profitable system. So spend 2-3 days on this, it will save you 2-3 months of wasted development. Loss functions and metrics. This is where most crypto bots fail silently. Loss function is what the model tries to optimize during the training. Metrics is how you measure the success. They are not the same things. For example, low root mean squared error does not guarantee high Sharpe or high returns during live trading. So in general, there is a hierarchy of metrics. First one is the loss function. In general, they tell your model where to go. There could be root mean squared error for regression or cross entropy for classification. Proxy or offline metrics. They are used to assess model performance during the backtesting. That could be more realistic metrics like Sharpe or backtesting PNL. And the last one is the business metrics or online metrics, the ones you care about. They are used to assess the model performance in a while. That could be realized Sharpe or realized PNL. So your process would be as follows. You start with defining the business metric or the online metric, the metric you actually actually care about, like for example, Sharpe ratio being greater than something. Then you work backwards to proxy metrics, and from proxy metrics you choose your loss function, the loss function that optimizes for that proxy or that have a high correlation with that proxy. The key lesson here is that wrong loss function probably equals right model, but for the wrong problem. Data and validation. In general, there are several data sources that you may use. Exchange APIs for price and volume, on-chain data for some fundamentals, data aggregators for additional features. Pick the ones that make your trading system successful. Your model could be perfect, but if your data is garbage, the output will also be garbage. Prepare your dataset, use ETL pipeline, extract, transform, load. Get the raw data, clean it, store it. But how much data is enough? Start small. Add more data until your loss stops improving. But remember that the key factor here is to have in your trading data multiple market regimes like bear, bull, sideways. Otherwise, your model will work only on the regimes it was trained on. And remember here that higher frequency captures more regime changes faster. Validation is really critical. Most backtests are bullshit because people use random trained test splits or just make incorrect assumptions. A proper validation framework aims to imitate the knowledge you have when operating in real life. Train on past, test on future. The time moves forward only. Data leakage kills models. Using tomorrow's price to predict today's is data leakage. Using data that's unavailable at prediction time is also a leakage. You must understand how you would use your model so to align it with how you would train your model. Baseline solution. Your complex machine learning system must beat simple alternatives, otherwise, why bother? A baseline is the simplest functional version, like an MVP. It tests if the problem is even solvable before building the complexity. Some baselines for crypto. The buy and hold strategy, your system must beat this. Momentum strategy, if price moves up, predict up. And the mean reversion strategy, if price spiked, predict drop. So your process would be as follows. Implement simple baselines. Test them on validation set. Your machine learning model must beat all of them. If a moving average crossover beats your neural network, then use moving average crossover. Complexity for complexity's sake is ego. Error analysis. Error analysis is how you understand what your model does wrong so you know what to fix. It's not about seeing a 60% accuracy, it's about discovering why the other 40% failed and what pattern exists in those failures. Those patterns would become your future roadmap for development and improvement. You do error analysis twice, first on your baseline to see where the simple model fails, and again on your ML model to refine it. In general, there are three techniques that you may use. The first one, learning curve analysis. Is your model even learning? Do you need more data, or do you need a different complexity of your model? The second one, residual analysis. Where does your model fail? High volatility regimes, news events, weekends, identify them. The third one, worst case analysis. What are the 10 biggest losses your model had? What are the patterns in them? After analyzing errors, identify the biggest failure patterns and use them to guide your next steps. Error analysis on baseline tells you what to build. Error analysis on your machine learning model tells you how to improve. Feature engineering. Mediocre model with great features beats the great model with poor features. Feature engineering is an iterative process that involves creating and testing new features or transforming the existing ones to improve the model performance. Start minimal. Price returns, volume, technical indicators like RSI or momentum, and then add based on your error analysis. If your model fails during volatility spikes, add volatility features. If your model fails during weekends, add day of the week as a feature. Feature engineering is an ongoing process. As objectives and data distributions evolves, features has to be continuously reviewed, updated, and versioned. So, okay, after you've done with the brainstorming on your features, next comes feature selection. Feature selection plays an important role in building the effective machine learning systems, offering both clear benefits and important trade-offs. So, for feature selection, you may use importance scores. Eliminate weak or redundant features. 10 or 20 strong features beat 100 mediocre ones. There are some criteria for determining the good features. The first one, they are available at the prediction time. Second, they are stable. And the third one, they are interpretable. Start with several features. Train, measure performance, add additional features based on your error analysis, cut anything that doesn't improve performance, and stay lean. Training pipeline. Training pipeline is a graph of steps that takes a full dataset as an input and produces the trained model as an output. It's high-level abstraction of the model itself. In general, there are two types of pipelines, the training one and the inference one. The training one runs on the historical data and updates the model weights. There are 7 key steps in the training pipeline. Data fetching. Pull historical price data from the exchanges. Preprocessing. Clean messy raw data. Training. Feed clean data into your algorithm. Evaluation. Run the model on the validation data and calculate metrics. Post-processing. Prepare your trained model for deployment. Reports. Create documentation of what happened. Training metrics, loss curves, error analysis, feature importance, worst predictions, packaging. Bundle everything needed for the deployment. Inference pipeline runs in real time, must be really fast, and makes predictions for real trading. These are separate pipelines. Test them both independently before deploying your model. Broken training pipeline means bad model. Broken inference pipeline means no trades. Monitoring. Your bot can break silently. Monitoring is survival. In general, there are 4 layers to consider. Layer 1, system health. Is your system or is your bot still running? Layer 2, data quality. Garbage in, garbage out. Layer 3, model performance. Is it still working? Model performance may deteriorate either due to data drift, input distribution changed, or concept drift, input-output relationship changed. And the last layer is business metrics. High accuracy doesn't necessarily convert to high business metrics or online metrics like actual return or P&L or something like that. So you need to monitor them as well, because at the end of the day we care about our online or business metrics. And the pro tip here is to log everything, every time step with features, confidence. When you lose money, you must understand what your model was thinking about. Integration. Congrats, you've built the model. Now it needs to connect to real world and execute trades. The integration pipeline looks as follows. Data flow, live market data to preprocessing, to feature calculation, to model prediction, to trade execution, to position tracking. Each step must work in real time. If any step breaks, the whole system fails. API design. Your model exposes prediction through an API. This API is some kind of a contract, so you need to version everything, model weights, data preprocessing logic, feature calculation, dependencies. Why? Same input must give same output every single time. When your bot loses 5 grams at 3 a.m., you need to replay exactly what happened. Execution layer. Model says buy Bitcoin. What happens next? You go and check account balance, calculate position size based on the risk management, check if market condition allow trade, spread, liquidity, send order to exchange, confirm the fill, and update position tracking. Integration isn't one thing, it's a glue that connects your model to money and allows you to track this money flow. Deployment. Now, how do you actually deploy these beasts? I would advise you to follow these steps. Define your latency requirements. If it's a day trading, maybe it's less than 1 second. If it's a swing trading, maybe it's less than 10 seconds. You have to know your numbers. Everything else flows from this. Choose your infrastructure. Cloud provider, AWS, GCP or Azure. Pick one based on cost or maybe based on familiarity. Compute. You have to determine it. For simple models like linear regression or XGBoost, it It could be CPU only for 20 to 30 bucks a month. For deep learning like LSTMs, transformers, or any other techniques, there could be the GPU instance needed for $2 to $3 per hour. Start small. A $30 a month instance would be enough for testing. Scale up only when proven profitable and or needed. Optimize costs. The math you need to do is to determine the model inference time, the predictions per day, and the total compute time. It could be that you need your model only running for 100 seconds a day. So, do you need a machine running for 24/7 or just these 100 seconds a day? You have to monitor resource usage. If there is a high utilization of your instance, then you need to upgrade. If there is a low utilization of your instance, then you may downgrade to save on your costs. Also account for monitoring overhead. Your monitoring system also needs resources. Logging prediction. It usually takes like 5% CPU overhead or something like that, and collecting metrics another 5% CPU overhead. So add 10 to 15 to your resource estimates. So the deployment rule would be to start with the smallest possible instance that meets your requirements. Don't optimize cost until you are proven with the real data that you need to. Remember how I said that 99% of crypto trading systems fail because they skip structure? Here is the structure for you. Phase 1, preparations. Problem space versus solution space and the design doc. Phase 2, early stage, loss functions, metrics, data invalidation, baseline solution. Phase 3, development, error analysis, feature engineering, training pipeline. Phase 4, production, monitoring, integration, and deployment. Most people will watch this and still jump into coding their transformers model. Don't be most people. In the next 2-3 days, write your problem definition, design your metrics, think of your validation schemas and your baselines, and only after that start building real machine learning systems. This framework is used by top tech companies building production machine learning system handling billions and billions of dollars. Use it, don't skip steps. And if you want to see me build using this particular framework, comment below. And of course, subscribe so you don't miss it. Thank you for watching.